So when we're communicating about compounds, there are a few ways that we can do that. What we want to be able to do is to start with individual elements and kind of build our way up to, if I give you a combination of elements, predicting what the structure will be, how those elements will combine to make a compound. So Lewis came up with Lewis dot structures or Lewis dot symbols, which are a pretty effective way of helping you understand how an element might get involved with other elements to make a compound. And so it's just kind of a visual way. In the context of ionic compounds, it's a visual way of doing what we've kind of already been doing. And what we've already been doing is focusing on how many electrons the element has and how many it needs to either gain or lose to make the same number as a noble gas. So a visual way of helping us do that is to look at the number of valence electrons and put a dot around the atom representing each one of those electrons. So each individual dot represents an electron. So for boron, it's in group 3A, which means it has 3 valence electrons. It also has an electron configuration that you can write out and recognize that 3 of its electrons are in the second energy level. There's no electrons in the third energy level. So the second level is its valence level. So it's got 3 of those. So I need to put 3 dots around it. How is that useful?
It counts up the electrons around the shield.
Yeah, it helps me to see how many valence electrons there are, but how does that help me to get a sense for what type of compounds boron might get involved with when it starts to connect with other atoms? Yeah, I can see that if for boron to be stable, what does it need to do? It needs to lose all 3. Right, so I see 3 dots and I see, okay, it needs to lose 3 to make the same number. By losing 3, it would make the same number as helium. Or it could pick up 5, which would give it the same number as neon. In either case, that's going to be difficult. Do you think it's going to be easier to lose 3 or pick up 5? The whole point of losing 3 or picking up 5 is to make the same number as a noble gas, right? Generally, if it makes the same number as a noble gas, that will make it more stable. But if it has to lose 3 electrons, and it only has 5 to begin with, so it's got 5 protons and 5 electrons to begin with, if it was neutral. If it were to lose 3 electrons, it would have 5 positives and 2 negatives. That's a pretty big imbalance. If I create a ratio of positive to negative charge that is really far from 1 and very imbalanced, that's not going to be a stable situation. If I have an atom with a very imbalanced ratio of positive and negative charge, in this case way more positive than negative, it's going to just start pulling electrons off of things because there's too much positive and not enough negative to balance that out. Right, so we have to think about not just the noble gas configuration, but also the ratio of charge imbalance. And for boron, it can't really effectively stay like this. So you won't really see a boron 3+ ion around. The ratio of positive to negative charge is imbalanced by more than a 2-to-1 ratio. Alternatively, if it were to pick up electrons, it would have to pick up 5 to make the same number as a noble gas. That also creates a 2-to-1 ratio of imbalance in charge, which is also going to make it pretty unstable. So not all of the elements on the periodic table are going to be able to form stable ions. What we'll find is only the elements that are here that are already very close in number to the noble gas will be able to lose 1 or 2 without creating a really big charge imbalance, a really big charge ratio that's really different from 1. Those ones will generally exist as charges. And likewise, the elements on the far side can pick up 1, maybe 2 electrons and make the same number of electrons as a noble gas without messing up the ratio too much. So let's compare aluminum with boron. Aluminum has 13 protons. and 13 electrons if it's neutral. So for aluminum, if it lost 3, 13 to 10. So for boron to lose 3, or for aluminum to lose 3, which is going to be easier to lose 3 electrons? Aluminum. When I see aluminum naturally, aluminum is found with a 3 plus charge. 13 to 10 ratio. If I divide 13 divided by 10, I get 1.3. Right? The ratio is close to a 1-to-1 ratio. It's not that imbalanced. So to lose 3 electrons, the larger the atom, the less imbalance will be created when that electron adjustment occurs. And the more likely it will be to give away electrons. And for this one, I get a ratio that's more than 2. So it's much more of an imbalance in the ratio of positive to negative charge. So we see, and we'll see as we go forward, the smaller the atom, the closer it is to the top of the periodic table, the less likely it is to be stable by losing electrons or gaining electrons. The harder it's going to be for that atom to stabilize this imbalance in charge that's created if it starts giving away a bunch of electrons or picking up electrons. But the Lewis dot symbol is just kind of a helpful visual way for us to see how many valence electrons there are and what would have to happen to it if it were going to pick up electrons or lose electrons and make the same number as a noble gas. So we already saw this in chapter 4. Here they're just saying that for elements that don't create a big charge imbalance, like sodium has 11, if it just gives one away, it will have 11 positives and 10 negatives. That gives it a +1 charge, but 11 to 10 ratio, still fairly balanced, so that's not really unstable. And that is the typical way we see sodium in nature. Likewise with chlorine, 17 protons. If it picks up 1 extra electron, that's 17 positives, 18 negatives. Again, a ratio that's pretty balanced, so that's typically how we see chlorine in nature. And so if you're looking at the Lewis dot symbols, what pattern do we see here is that depending on the group number, 1A, 2A, 3A, 4A, etc., for the main group elements, not worrying about the transition nodes for now, but for the main group elements, we can quickly see visually that the number of valence electrons should be equal to the column. Right? So we don't necessarily have to, at least for the main group elements, we don't have to draw out the electron configuration and see how many of those electrons are in the outermost principal energy level. We know based on that, usually a Roman numeral or Arabic numeral at the top with the letter A next to it, that tells me how many valence electrons the atom would have if it were neutral, and then I can make the dots around it to show those electrons visually if that's helpful. So just a couple examples. Generally, sometimes you'll see the electrons paired up. Sometimes you'll see them spread out. I don't really care too much about that. But when you have Lewis symbols for some element, usually there are kind of like 4 quadrants around there. So you wouldn't want to put 8 electrons around like this. Don't just spread them out from one another, because we know when we have orbitals full, they pair up in the orbitals. So when we draw our dots, we want to draw them in pairs. So if I have an element with 8 dots, I would pair them up on the 4 sides of that atom to kind of show somewhat that they're paired up in orbitals and they're not just individually all spread out around the atom. So, I mean, the Lewis dot symbol is not very complicated. You just have to figure out how many valence electrons there are and then put them in as dots. Then if you have an ion, you can also show that with dots. Right? So for an element that's losing electrons, usually we just show that dot not there anymore. We know that there's now 8 dots underneath. You can show those if you want to. That would be okay. Right? Because sodium has 1 valence electron at the 3rd energy level. If it loses it, then it has the 2nd energy level still underneath with 8 electrons. So now Once that third energy level electron's gone, now the second energy level electrons become the valence electrons. So you can put 8 dots around there if you want. That's okay. Without them, that's also okay because it's showing that that entire third energy level is gone. The oxygen, to be stable, it needs to pick up 2 electrons to make the same number as a noble gas. So instead of having 6, usually we would put in 8 around there if it has a -2 charge. Usually the students don't have too much trouble with the Lewis dots symbols. So you can see, just if you look quickly at these 2 examples in the textbook, I'm not going to go through them, but if you have questions about those, or if you feel unsure about them, let me know. I'll discuss them with you individually. But this just, if I give you an element, even if it has a charge, you should be able to draw the Lewis dot symbol with the right number of dots around the symbol. Or if I give you the symbol, you should be able, and the dots, you should be able to count how many dots there are and determine what the charge on that element should be if I give you the symbol and the dots. So it's actually pretty straightforward, simple math. So let's do some examples that are a little bit more complicated. So here, I want to draw the Lewis symbol and predict the most commonly found form for the element in nature. So hydrogen, if it's neutral, how many dots should I put around it? 1. It only has 1 electron if it's neutral because it has 1 proton, right? So what's its most commonly found form in nature? The idea is, can I give it a noble gas configuration? And if so, how can I do that without creating a lot of charge imbalance? So the nearest noble gas is helium. If I want to make it into its most stable form in nature, I want to give it 2 valence electrons, the same number as helium. However, that will create, since it only has 1 positive charge in its nucleus and 2 negatives now, that creates a charge imbalance. It's a 2-to-1 ratio. It's not a very balanced ratio. So it's actually pretty unstable to create a hydrogen anion. So what does hydrogen need to do to keep 2 valence electrons but not have this big charge imbalance? Yeah, it needs to share. Right? So if I take 2 hydrogens, each with 1 valence electron, now the electrons can get in an orbital. Instead of having that 1s orbital where the electron is, the 2 hydrogens can overlap their 1s orbitals. And now, when orbitals overlap, what I get is a new orbital. The orbitals add together to create what's called a molecular orbital. This is an orbital. It's not like a 1s or a 2s or a 2p that are atomic orbitals, orbitals that are only around 1 atom. This is a molecular orbital, so it's the same thing. It's an orbital, but it extends over more than 1 atom. So the electron density, or the probability for electron density in this orbital, is everywhere over both atoms instead of just like maybe a sphere surrounding 1 atom. And that allows the electron density to be primarily between the nuclei. This makes a stable situation because the positive charge is in the nucleus and the negative charge is primarily between them, and I'm forming lots of nice attractions between the negatives and positives. Plus, both hydrogens get to experience the same electron configuration as a noble gas because both hydrogens can feel the presence of 2 electrons around them. We'll talk much more about situations like this where electrons are shared because these are covalent bonds rather than ionic bonds. But that's usually what we see hydrogen doing, sharing electrons so it can get the same number as a noble gas without creating a big charge imbalance because I still have the same number of positives as I have negatives in this arrangement. What if I had O3 minus? What would that look like? Well, I would have an oxygen. How many dots should I put around it? O3 minus? 1 dot. Normally, oxygen would have 6 dots, right? Because it's in group 6A. So if I'm adding 3 negatives, the first 2 complete that level. The 2p. the next electron has to go into the 3s. So now if I put 3 electrons in, the second energy level is no longer my valence level. Now the third energy level is my valence level, and I have 1 electron in the third level, so I need 1 dot. Right? The Lewis dot symbol does not show core electrons. It only shows valence electrons. So if I put so many electrons in that I start putting them in a whole new level, the old electrons that were there aren't valence electrons anymore. Only the electrons in the outermost level, and the oxygen 3- would have 1. Is that going to be a stable form for oxygen? No, it's not. It doesn't want to do that. It needs a noble gas configuration. So the most stable form would be this, which would be an oxygen 2-. Yes?
On the test, does it matter how we arrange the dots? Does it have some features?
No, not other than if you have a bunch of them, try to put them in pairs. All right, what would the calcium 3+ look like? How many dots would you have around that? So a neutral calcium has 2 dots, right? So how do I take away 3 if I'm only starting with 2? Well, I have to remember that the 2 dots are the valence electrons. Those are in the 4s. So yeah, I would take those away first. What's underneath then? The 3p and the 3s, which would be a total of 8. So once I remove the 2 from the 4th energy level, now the 3rd level is my valence level, and if I still have to remove 1 more, it would look like that. I would have 7 dots. Is that going to be stable? No. Typically, calcium should have a 2+ charge because I want to keep that 8th dot in there and give it the same number of electrons as argon. So calcium 3+ is not something you're going to find readily in nature. Iron 3+ is a tricky one. The transition metals often have a weird number of valence electrons. So if we wanted to work this one out, we would start with the iron, which would have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. The 6th element over in the D block. If I want to remove 3 electrons, the first 2 I remove come from the 4s. Then the 3rd one I remove would come from the 3rd energy level. So how many valence electrons would that have? Well, the 3rd level is my outermost level. All the electrons in the 3rd level then are valence electrons. So I have to add those up, and I get 13, right? So I would need 13 dots. Well, that's weird. That looks weird. So for the transition metals, usually you won't see them shown with the dots because it just looks like a bunch of dots jammed in there. It's not really useful visually to see them. But that is what it would look like if you did have that situation. Potassium negative, how many dots should that have? Two. Normally potassium has 1. I'm adding 1 more. Is that a stable form for potassium? No, I mean it does give it a complete subshell, but that's not nearly as stabilizing as giving it the same number of electrons as a noble gas. So instead, we would see potassium with a plus charge instead of a negative charge. And then the argon is in group 8A. It's neutral. We don't have to adjust its number of electrons. So being a group 8A element, I would just put 8 valence electrons around it and give it 8 dots. That is how argon is found in nature.